Instead of mapping summed diffraction images from selected regions in the spatial domain, we might want to do the opposite and map the variation in signal intensity of a feature or features in the diffraction domain. Let's go back to the copper grain boundary demo dataset. Use the picker tool and extract a diffraction pattern from one of the grains in the data cube. Use an oval ROI to select the transmitted or unscattered spot in the diffraction pattern. Now go to the SI menu, go to the Map submenu and choose Signal. Digital Micrograph calculates and plots an intensity map and displays the results in a new image called Signal Integral in the active workspace. The intensity of each pixel in the map is the summed intensity of the pixels enclosed by our oval ROI in the diffraction pattern and corresponding to the equivalent spatial domain pixel in the 4D data cube. One of the most common imaging modes in TEM is bright field imaging, where an objective aperture is used to select just the unscattered electron beam for image formation. The signal map we just generated is exactly the same, but is done virtually without the need for a physical aperture in the microscope. The oval ROI is acting as a virtual objective aperture, and the map we have is a virtual bright field image. Another very common imaging mode is dark field imaging. To form a dark field image, diffraction shift controls on the microscope are used to move the primary beam outside of the acceptance angle of the objective aperture and move a diffracted beam to the aperture center instead. This kind of imaging is useful in studying crystal defects and for imaging of specific crystallographic phases. We can form a virtual dark field image from the 4D STEM data in almost the same way as the virtual bright field image. Use the picker tool again and extract another diffraction pattern from the copper dataset. Draw an oval ROI on the diffraction image, but now, instead of enclosing the primary beam, choose one of the diffraction spots. Go to the SI menu again and select Map Signal. This time, our map is a virtual dark field image. As I selected a reflection that corresponds only to one of the 3 grains in the sample, only that specific grain shows bright contrast in the map. The other 2 grains that have different orientations are dark. As before, we aren't limited to a specific shape or only one ROI to do this. We can select 2 or more ROIs and generate a dark field image from those. Remember to hold the Shift key down to draw the second ROI. Once you are done, go to the Map section in the SI menu again. Now, instead of choosing Signal, choose Signal Dynamic to create a dynamically linked signal integral. Any changes in the selection ROIs is immediately reflected in an updated signal integral. See how the contrast changes as I move the ROI to different reflections. The signal integration region can also be set with the Mask tool. Right-click to show the Tools menu again, but instead of selecting the ROI tool, select the Mask tool. Choose the Bandpass mask and left-click on the diffraction pattern. I can change both the inner and outer diameter of this mask. And once I'm happy with the angular selection, I go to the SI menu and generate a map as before. Using the bandpass mask to generate maps like this is equivalent to forming virtual STEM images with virtual annular detectors. Some of the most common detectors are annular bright field detectors, annular dark field detectors, and high angle annular dark field detectors. The angular range of the detector determines the type of electron scattering collected, and therefore the contrast formation mechanism in the image from that detector. Virtual equivalents to any of these images can be formed using the bandpass mask on 4D STEM data. Now that we've covered the basics, let's move on to some more advanced tricks again. Digital micrograph will always center a mask at the center of an image. The image center doesn't always correspond to the diffraction pattern center. The mask center can be adjusted easily using the centering tool. Just right-click on the diffraction pattern, select the DiffPack Assign Center tool, and left-click on the diffraction image to adjust the center. Another visualization tool for 4D STEM data is the Slice tool, which can be accessed under the Display tab. The contrast we see in the SI data object is an integral of the angular range in 2 dimensions. The Slice tool allows us to change the angular range that is being used to generate this contrast. The Slice palette is populated with sliders when an SI data cube is selected in the software. So to start with, just make sure the 4D data cube is the frontmost window in DM. The contents of the Slice tool now indicate the angular range to be summed and displayed in the diffraction image window. The top pair of sliders indicate the range and width in the diffraction space X dimension, while the bottom pair indicate the range and width in the diffraction space Y dimension. Look at how the contrast in the 4D image changes as I move the sliders left and right. If you want to see the specific angular range that is being summed on the diffraction data itself, use the picker tool and extract a diffraction image. Make sure the diffraction image is frontmost, then click Show Range in the Slice palette. Enabling Show Range places a rectangular ROI on the diffraction pattern. This ROI is moved and resized in response to changes in the Slice tool sliders. The range can also be controlled by moving or resizing the ROI itself. To remove the Slice ROI, just delete it or uncheck the Show Range box in the Slice palette.